Hello, this is Richard Cole. I'm going to be giving a series of videos on the pumping lemma for regular languages. I'm a faculty member at the Courant Institute at New York University. If you want to see more details, you can consult my webpage. Among other things, I have taught the undergraduate course on theory of computing at NYU multiple times. My research interest is in the area of the design and analysis of algorithms. And more particularly, for the last 12 plus years, I have worked in the area of algorithmic economics and game theory. And in particular, I'm interested in algorithmic explanations for economic phenomena, such as why the invisible hand of the market manages to balance supply and demand. That is, manages to find prices that balance supply and demand. And fundamentally, this is a question about how efficiently one can transfer information within a market, within an economic market. Okay, at this point, you should have seen multiple examples of regular languages and how to demonstrate membership, how to demonstrate membership in such a language using DFAs and NFAs, and also how to represent such languages using regular expressions. However, many, and indeed most languages are not regular. And this sequence of videos is going to be about giving you a tool to demonstrate in a convincing way that particular languages are not regular. So let's just see a few examples of languages that are not regular. For instance, we might have L consists of strings which start with some number of A's and are followed with an equal number of B's. So this is a language and it's not regular. And intuitively, the reason is, if you wanted to recognize a string of this sort, once you'd finished reading the A's, you'd have to know how many A's you had read. And in order to do that, it would seem, if you were using a DFA, that you would need a state for each possible number of A's. But since you could have any number of A's, this isn't a finite automata. Another non-regular language that we're going to be seeing is a language that consists of a repetition of a string. So W is just some string of A's and B's, and then our string is W followed by W. And again, to check that a string is in this form, it would seem you need to remember the first W in order to check that the second part of the string matches the first part. And once more, it doesn't seem that you can do this for every possible such string with a finite amount of memory, a finite amount of states. And for a very different language, very different looking language, this is a language over a single character alphabet, but a language which has relatively few strings. It's still an infinite number of strings. But here the strings consist of a sequence of A's where the number of A's in the sequence is a prime number. So 3 A's would be a string in the language, 17 A's would be a string in the language, but 16 A's would not be a string in a language. And again, this seems like something just too complicated to recognize with finite automata. At this point, probably don't see how to pull all of these things together, but what these videos are going to be about is providing you with the tool to be able to show that these languages and many other languages are not regular.